for the recording, let me just go back and review. What we're doing is just reviewing this problem. First term, first item, second, third. We're down to the fourth step here. And the fourth step, again, once we have the second derivative, is to, and again, I can't hear you because of the fan. Okay. Of what? Yeah, it's actually of one less than what you're working on. Okay, so it's the critical numbers of the first derivative, which happen to be the zeros of what? Of what you're working on. Okay, good. Second derivative. In other words, we set the second derivative equal to 0. Now, what do the zeros of the second derivative tell us? Thank you. Possible inflection points. And inflection points tell us changes in what? Concavity, yeah. Concavity on or of the first of the function. Okay. So the second derivative shows change in concavity. Now remember, a lot of what we're doing in problems like this, we really can look at the graph to come up with answers. Does this function have any extremity or any extreme points? Look at the graph. Does it go up and then down? Sure, it has one. But we need to get beyond just seeing if there is one. We want to know where it is. And the only way to get to an exact answer is analytically, and this is the analytical approach that we're talking about. Visually, on the graph, we can see a lot of the information we want, but we can't pinpoint exact values. Why are those important? Well, a lot of times those exact values are then used later on in the problem. And if I round the answer to 3 decimal places, isn't that good enough? I mean, money is only rounded to 2 decimal places, so if I round to 3, but what if that value that you round to 3 decimal places is going to be squared or cubed or some other power applied to it or some square root? And that value is what you're going to report to your CEO as to whether or not this function, this model that you've developed, is going to give the company a profit or a loss. A few pennies here and there don't make a whole lot of difference to us, but when they get multiplied and raised to powers and evaluated in many more other ways, they can become billions of dollars. I'm sure some of you have heard about ways of scamming. You just kind of skim off the pennies every now and then, and after you do that with a whole bank's account, you got $1 million after a while. And so if you do that unintentionally because you rounded the numbers and didn't think to always put in exact values, you could be in trouble, okay? And I don't want to hear your names in the newspaper in that way, okay? Positive ways, yes, but not in that way. So it's important that we go through and understand this so we get exact values so we can use those exact values in our calculations. Well, another thing of importance to us is this thing called points of inflection. Now, the inflection points, and that's about as much as we need to know at this point. The inflection point, I think we've talked about this maybe, talked around about it. The inflection point is where the concavity changes. And I think we talked about that. We've identified it graphically. But we need to, again, know how to develop these or define these with exact values. So let's look then further here. If the graph of a continuous function has a tangent line at a point where its concavity changes from upward to downward, from concave up to concave down or vice versa, the point where concavity changes is known as the point of inflection. Properties of the points of inflection. If this is a point of inflection, C is the input, F of C is the output, then the second derivative at that point is 0 or it doesn't exist. Keep that in mind. Or it doesn't exist. We can always have that possibility. That's kind of a formal definition of what we've been talking around about. Second derivative test. If I know that I have some extrema, so from the first derivative, I found my critical numbers of my function and I found my zeros of the first derivative, then if I put that value where that zero, that critical number occurs, and the second derivative is positive, remember positive means that it's concave up. If it's concave up, it has a minimum. If it's a second derivative value, when you put that critical number in from the function is negative, you know it's concave down, you know you have a maximum. If it is equal to 0, we don't know anything. We've got to investigate it further. The inflection point is somewhere between where it's concave up and where it's concave down. So somewhere in there would be our critical number of a function. So let's look at finding the points of inflection. The points of inflection come from what? First derivative or second derivative? So in order to get to the second derivative, we have to first do the first derivative. So there's no way around this. So we're going to determine the first derivative of this function. Now, how you go about finding this first derivative is up to you. I can think of a couple of ways I could do this. One might be to expand the cube of that binomial, multiply this out, and then multiply through by x. Giving myself just a degree 4 polynomial function. Now, if you like to, cube a binomial and do that, you have the choice. If you decide on some function you don't want to do that, then another one we could use is the power rule, and then we'd have to use on this factor, this is simple enough, but we would have to use the chain rule. So I'm going to do the second one because that's a good practice for our derivative work. Again, if you want to multiply that out and then get to it, that's fine too. So we've got the first factor times the derivative with respect to x of the second factor plus the second factor times the derivative with respect to x of the first factor. Let me just digress just a little bit. What does that mean? Say it again, Aaron. Yeah, oh wait. What are you oh waiting about? What do you see there? Yeah. Unfortunately, I had more than one person write stuff like this for the last quiz. When we have this notation, this is, as Aaron was trying to say, it is x times the derivative of y with respect to x. Take that and multiply it to this. Why? Because that y represents a function. I don't know what function it is, but whoever wrote this thinks that there's another function sitting out there called y equals, because that's the way it's written. What we should write is what we have over here. I want the derivative of this output with respect to x. So don't, if you're guilty of this, if you did this on the quiz, you're going to see some marks, so just be prepared. This is improper, and it's like you're being so picky. It's not so picky if I don't know a language, but I use some terms because I memorized some phrases, but I don't have a clue what I'm saying. Do you realize you can get into big trouble for that too? It's the same thing here. This is a language. And if you don't understand the language, you don't understand the notation, you really don't understand the mathematics behind it. We're talking about some value, some function, such as, you know, over here that you're taking the derivative of, and then you're multiplying it times that. Okay, well, just a little bit of that. So I've got x times, now I've got the derivative of a cube of another function, so I've got to use the chain rule. Some of you missed this on the quiz. And then I've got to take the derivative with respect to that inside function. Again, some of you are not writing out all the derivatives. Will you hear from me on that? Yeah, you will. You will. Plus x minus 4 to the third power times the derivative of x with respect to itself, and it's just 1. So let's see, I've got x, actually we can make that 3x while we're at it. 3x, x minus 4 quantity squared, this is going to be times 1, plus x minus 4 quantity cubed. So, you know, here again now, what are we going for? Are we looking for extrema? Doesn't say, okay? You can go ahead and do that if you wish, but it's not asking for extrema. If we wanted extrema, we would have to stop and take the zeros of this. But we're looking for points of inflection, and that comes from the second derivative. So, you know, how you finish this up is up to you. You might say, well, I'd like to factor out an x minus 4 quantity squared, and that gives me 3x plus x minus 4. Or simply x minus 4 quantity squared times 4x minus 4. That may be where you want to go with that. You may want to leave it like this and work it from there. I think I'm going to even do one more step and make it 4 times the quantity. Let me put that 4 out in front. 4 times the quantity, because I'm taking a 4 out of that last one there. Now I need to find the second derivative. It's just taking the derivative of the, if you want, go ahead and expand it, make it into a polynomial of degree 3, if you wish. But I think I'm going to opt for the product rule again. So I have the first factor times the derivative with respect to x of the second factor, plus the second factor times the derivative with respect to x of the first factor. And I guess I need, you know what, I'm going to take that out of there. Don't really need to have that. And then I have 4 times that whole thing. Taking the 4 out in front of the whole product of these, as if there were brackets there. Okay, so let's see. X minus 4, quantity squared, times 1, plus x minus 1. And now I've got the chain rule I'm going to have to use over here. So let's see, that's going to be 2 times x minus 4 times the derivative with respect to x of x minus 4. When I graded your quizzes, I noticed that, you know, a lot of you have a lot of good stuff going on, but because you don't put in enough brackets and you don't follow through with the negatives and you don't tell yourself what derivatives you're taking, you're dropping those, and you're dropping points along the way too. Okay, so I've got 4, and let's see, this is x minus 4 quantity squared, plus, let's see, this will be 2 times x minus 1 times x minus 4 times 1. I'm going to opt not to put that in. And now that I now that I have that done, I guess I could factor in an x minus 4, couldn't I? You know, it depends on how